Okay, so ready to dive into something kind of mind-blowing, trying to actually measure complexity.
Sounds ambitious.
It is. And you know what's surprisingly helpful in this quest? A good old cup of coffee.
You're not just talking about procrastination fuel, are you?
Not this time, though a good cup never hurts. But no, this is serious science.
Okay, I'm intrigued. Hit me with it.
So we're looking at this research paper, quantifying the rise and fall of complexity in closed systems.
Catchy title.
Right. But the best part, the subtitle, the Coffee Automaton.
Okay, now I'm fully on board. Tell me more about this Coffee Automaton.
Well, it's the brainchild of Aronson, Carroll, and Ullalette.
Familiar with their work. They're always onto something interesting.
Right, and their big goal here is to figure out how we can actually put a number on complexity, how it changes over time, how to track those shifts.
Ambitious, for sure. Why is this so important, though? Why does it matter if we can measure complexity?
Because it gets at the heart of, well, everything. Think about it, the early universe. Pretty simple state, right?
From what we understand, yeah.
And then the far future, also probably pretty simple. Kind of a bummer, actually, when you think about heat death and all that.
Not the most cheerful thought, no.
But right here, right now, in between, that's where things get interesting.
Stars, planets, life. Us sitting here talking about it.
Exactly. This paper is trying to figure out how we can track those shifts from simple to complex and back again.
Okay, you've officially hooked me.
Yeah.
But how do you go from swirling cream to, like, equations and algorithms? It's a bit of a leap.
Fair enough. So these researchers, they built a computer simulation, a cellular automaton, if you want to get fancy, that acts like a pixelated cup of coffee.
A pixelated coffee cup. That's our stand-in for the universe.
In a way, yeah. And they actually made two versions. One where the cream particles politely move one at a time, no bumping into each other.
Sounds a bit too utopian for real life, don't you think?
Exactly, which is why they made the second version where particles collide more like they do in, well, reality.
Chaos reigns.
Pretty much. But that's the whole point, right? To see how those interactions affect complexity.
Makes sense. But then there's the whole issue of measuring this complexity. Like, we can all agree that cream swirling in coffee looks more complex than just a perfectly blended beige.
Right, but how do you put a number on that?
Exactly. And these researchers, they didn't just want to rely on our intuition. So they explored 4 different ways to try and quantify complexity, each with its own pros and cons.
Okay, a 4-way complexity showdown. I'm in. Break it down for me.
All right, so first up, we have what's called apparent complexity.
Yeah.
Think of it like squinting at a blurry picture.
I can still kind of make out the shapes.
Exactly. You get the gist.
Mm-hmm.
So this measure focuses on how much info you need just to describe those big picture elements.
So I don't need to know where every single molecule of cream is to know if my coffee's mixed or not.
Precisely. It's about the big picture. Now, the next contender, sophistication. This gets trickier.
Oh, boy. How so?
This one's all about figuring out how much meaningful structure there is in a system versus just random noise. Like, picture a monkey randomly hitting keys on a keyboard.
Versus, say, Shakespeare writing a sonnet.
You got it. Both involve a bunch of letters, but one's clearly got more structure, more meaning baked in.
Sounds incredibly difficult to measure, though. Like, how do you even begin to define what's meaningful?
That right there is one of the big challenges in this whole field. But let's move on to contender number 3. Logical depth.
Lay on me.
Imagine you've got a computer program that can describe our coffee mixing perfectly, right?
Okay, got it.
Logical depth asks, how long does it take to actually run that program?
So a short, simple program, that probably means a simple system.
Maybe. But it could also be a sign of a really cleverly designed complex system all packed down into something deceptively short.
Sneaky. I like it. Okay, what about our final contender? What's left to throw into the ring?
Last one's a doozy, light cone complexity. And this one, it gets a little more abstract.
I'm ready. Hit me.
It's all about how much the past of a system can tell us about its future.
So kind of like if we know the weather patterns from the last few weeks, we can make better guesses about next week.
Exactly. It's great for predictions. Less useful, maybe, for judging how complex a single moment in time is.
Okay, so 4 very different ways to measure complexity. Kind of like trying on different pairs of glasses to see which one gives you the clearest view. Which one did these researchers end up going with?
They decided to go with the souped-up version of apparent complexity.
Interesting. Why that one?
Well, for one thing, it's actually something we can measure.
Always a good starting point in science.
Right. Plus, it kind of mirrors how our brains naturally work anyway. We latch onto patterns, try to find order even in chaos. And they figured out a really clever way to use file compression to basically put a number on how visually complex those simulated coffee swirls were.
File compression. You mean like I'm zipping a folder on my computer?
Exactly.
Hmm.
Think about it, a more complex image. Even if you smooth out some details, it still needs more data to describe it, harder to compress.
So a simple uniform image is like my sock drawer, perfectly organized, easy to compress. But a complex, swirly image, that's like my kid's toy closet. Good luck zipping that up neatly.
A chaotic masterpiece, which is what they were going for here, right? Using this compression method to track how complexity evolves in those simulated coffee cups.
Okay, but back to those two versions for a sec. Did the results actually show what we intuitively see when we're like actually watching cream swirl in coffee? Does the complexity peak and then fade as everything mixes together?
Yeah, that's the really cool part. So in both simulations, the one where the particles are all polite and the one where they're bumping into each other, the complexity, it did rise and then fall as the cream particles spread out.
Just like we thought. But I have a feeling there's a plot twist brewing here.
There's always a plot twist. Okay, so here's where the Rude simulation, the one with the collisions, gets really interesting. That version, it stayed complex for way longer, like significantly longer.
So those collisions, that rudeness, as we're calling it, it actually makes for a more interesting, more persistent kind of complexity. Makes you wonder if maybe out there in the universe, that's what's going on. Just particles bumping into each other, keeping things interesting.
And the more of those particles they added, the longer it took to reach peak complexity. It's like, give it time, things will mix eventually.
So if we think of the universe as this giant coffee cup, and why not? It kind of makes sense that it took billions of years for things to really get cooking, stars forming, galaxies swirling, and eventually, well, here we are talking about it.
It's a process, that's for sure. Not an overnight success story, this whole universe thing.
But hold on, we've gone full-on rude simulation here. What about those polite particles just doing their own thing? Did their version of complexity ever really amount to anything?
See, that's the really fascinating thing when you compare those two models.
Ah.
Even with, like, all the time in the world, those politely diffusing particles, they never actually hit the same level of complexity as the rude ones. And the researchers were able to actually prove this mathematically.
Mathematically? How so?
So because the particles in that polite simulation, they don't directly interact, right? It means the whole system stays predictable in a way that the rude version just isn't. You only really need information about one dimension to, like, fundamentally understand the whole thing. It's missing that extra layer of chaos that you get with those real-world messy interactions.
So in this case, more chaos actually equals more complexity. But even with all that chaos, were there any hints about whether complexity itself has limits? Like, is there a ceiling somewhere?
Now, that is a question with some seriously big implications. And it's not an easy one to answer. But interestingly, when they looked at how the maximum complexity changed as they made their simulation bigger, I can imagine, like, supersizing our coffee cup. It didn't quite scale the way you might think it would.
Okay, so you're saying if I double the size of my coffee cup, double the cream, I don't get double the complexity.
Not quite. It seems like that maximum complexity a system could hit, it was more related to, like, the width of the coffee cup, not the overall area.
So it's not just about having more stuff to be complex with. There's something about those boundaries, those edges where those initial interactions happen that seems to really matter. It's like complexity, it likes to spread out, but only within certain limits.
It's like that first point of contact, right? Between the coffee and the cream, that's where the real action is.
Yeah.
It's a fascinating insight.
Okay, I gotta ask, I get how this whole file compression thing works for measuring complexity in like a visual sense, but weren't there concerns about that being thrown off by the resolution of the simulation itself? Like, what if you zoomed in too far or not far enough when you were looking at those pixelated swirls? Would that change the measurement?
You're thinking like a true scientist. And you know what? They thought about that too. They knew that if they were going to claim they could really measure complexity, they had to make sure it wasn't just some weird side effect of how they were looking at the data.
So how did they address that? Did they have to go back and redesign the whole simulation from scratch?
Not a complete redesign, no, but they definitely had to get clever. So instead of just sticking with a few, like, broad categories for measuring the complexity, they created this whole more nuanced system, kind of like adding more shades of gray to the picture, you know?
Adding more shades of gray to, like, literally the picture of the coffee cup or...
Well, Kind of both, actually. But yeah, more like a metaphorical picture of complexity, adding more detail, more ways to differentiate between those pixelated swirls.
So more fine-grained approach.
Exactly. And not just that, they actually developed a whole new algorithm to help them smooth out any weird cases that might have been like artificially bumping up those complexity scores. Think of it this way: you wouldn't judge like a painting just by the number of colors the artist used, right?
Definitely not. It's about how those colors are arranged, the brushstrokes, the composition, all of it.
Exactly. And that's what they were going for here too, a more like holistic measure.
Okay, so always good to double check your work, especially when you're dealing with something as slippery as complexity. But after all those tweaks and refinements, did their findings hold up?
They did. Yeah, the whole thing about those rude interactions, the collisions leading to a more persistent complexity, it all held up. It wasn't just some like fluke of their methods or anything. Those colliding particles, they were the real deal when it came to creating interesting, long-lasting patterns.
And what about our polite little particles just bouncing around merrily? Did those refinements to the measurement at least give their complexity scores like a little boost?
You'd think so, right?
Right.
But that's the thing. If anything, those adjustments actually made the polite particle results even more clear-cut. They really did just stay remarkably simple, which kind of confirms what the math was already suggesting. Without those interactions, you just don't get that same emergent complexity.
So no matter how you slice it, those collisions really are where it's at.
Seems like it.
So to sum it all up, we're potentially looking at a whole new way to measure complexity, right? And not just in our metaphorical coffee cups, but maybe in the universe itself. That's kind of a big deal.
It is. And maybe, even more important than that, this whole research project, it encourages us to like think differently about the world around us. You know, it's highlighting how these really simple rules, when you combine them with just a bit of interaction, maybe a good dose of rudeness, they can lead to these incredibly complex and interesting outcomes.
Makes you wonder what other hidden complexities are out there just swirling around, waiting to be discovered. What seemingly mundane thing might hold the key to some big cosmic mystery just because we haven't looked at it in the right way yet?
And that's what makes this field so exciting. Every answer just opens up a whole new set of questions. We've really only just scratched the surface here.
So, to everyone listening, next time you're enjoying your morning coffee, take a moment to appreciate those mesmerizing swirls, right? They're not just a sign of a good mix, but a subtle reminder of that dance between simplicity and chaos that's playing out all around us, all the time.
Who knows? Maybe one of our listeners will be the one to make that next big breakthrough in understanding complexity.
And if you do, we'd love to have you back on the show to tell us all about it. Until then, keep those coffee cups swirling and those minds exploring.